Hi everyone. This lecture I'll talk about Gaussian integration. I hope it will be a quick lecture, but it will help in solving many problems. The Gaussian or the normal distribution or the bell curve is a very important object in probability theory and also in quantum mechanics. In relation, the Gaussian is related to the problem of the harmonic oscillator. All right, so for a Hamiltonian of the form p squared divided by 2 times the mass plus x squared multiplied by a constant here, the solution of this problem with p equals to I h bar, negative of that, the spatial derivative, it has as a solution for the fundamental state a Gaussian distribution. Right? So this quantum mechanical problem is very, very important in quantum mechanics. It can be used to model many things, and Gaussian integration is a key ingredient, is a fundamental ingredient in Feynman formulation of quantum mechanics. Usually you want to find out a Gaussian or a form of Gaussians which you can integrate and find results. But for now, we are interested in calculating, for instance, an average of x as an exercise I previously asked you to solve, x squared and all that for a Gaussian wave packet, or p squared and p and all that for a Gaussian wave packet. So I will describe in general the Gaussian integration. All right, it's a very interesting topic in mathematics and in quantum mechanics. It is instrumental. It's a very important mathematical tool. All right. So first of all, you can ask, what is the result of this integral? Call it the integral from minus infinity to infinity. This integral, it is a symmetric function. All right. So as you can see, if you integrate x, the exponential of minus x squared dx, it's of course a well-defined differential here, and you can change variables, but you can also use a more intuitive approach. This is an odd function because if you replace x by minus x, you reverse the sign of the integral. And in this case, by symmetry, you can show it already has a result equal to 0. All right. So this is an even function. This is an odd function. If you plug in odd powers and odd here and odd 1, 3, 5, and odd numbers, it goes to 0. So we are interested in eventually even powers here. But first, we need to show what is the value of this integral. I don't know if it was Gauss who did it first, but the guy who did it was a very smart person. He thought about squaring this integral. So he has this thing here, this object. The integral of e to the minus x squared dx is a numerical value squared. But since the integral is squared is the integral multiplied by itself, in this case, because you're squaring, you can change the symbol here to y squared dy from minus infinity to infinity. it is the same thing. It's the same number. You are squaring the integral. Now you have a double integral in the variables x and y. They are independent. So this is the same number as here, but written with distinct dummy variable. The integration variable is also called a dummy variable because after you integrate that, it vanishes from your result. It does not appear anymore. All right? So this is what this smart guy did. He took the square of this integral and it will lead you to this form of the integral. All right? In the end, it's just to take the square root of the value you find, you have found in the end, and you have the value for the integral. So the integral squared corresponds to integral of e to the minus x squared minus y squared. Both integrands must be integrated from minus infinity to infinity, dx and dy. But this is an abstract variable. It does not need to be the x direction and the y direction, but formally it is the same as a double integral in the plane. So if you are integrating in a plane, you can just perform a variable change. Call x equals to r cos of some theta, and y equals to r sin of theta. This is a change variable. You'll find out that dx dy is equal to r dr d theta, and the integral limits for r, it goes from 0 to infinity, and for theta it goes from 0 to 2 pi, right? So it can now be integrated because minus x squared minus y squared, if you remember, x squared plus y squared is just r squared. All right, so this is a variable change, and if you look at that, you'll find out that this integral is converted to a double integral. It's still a double integral from 0 to infinity in the variable r, from 0 to 2 pi in the variable theta, e to the minus r squared r dr d theta. And integrating the theta will give you 2 pi. While r dr is just, we are missing a factor of 2. If you plug in 2 here, we can divide the integrand by 2. 2r dr is just the differential for r squared. So it gives you an exact integral, all right? So you divide it by 2 and you integrate e to the minus r squared multiplying 2r dr. You have e to the minus r squared from 0 to infinity. A minus sign emerges also because this exponent here, when you differentiate, you get a minus sign here. So to be precise, you can define minus r squared equals to, or r squared equals to u, and you'll find e to the minus u, and r dr multiplied by 2 is equal to the differential, du. This is exactly solvable. You can then replace u by r squared again, and in this interval it gives you 1 positive 1. So the 2 cancels out here, and this integral corresponds to exactly pi, right? And then you have found the value for the Gaussian integral, right? The Gaussian integral now is pi, the square root of pi to be precise. So the integral of e to the minus x squared dx from minus infinity to infinity, it is equal to the square root of pi, because we have found the value for the squared integral. So we need to take the square root, and this is the integral value. All right. But now you can try to find out a more general integral, which can be converted to this one. All right. Say you want to integrate minus ax squared plus bx. That's what you wanted to integrate right now. You want to integrate this thing here. So, with respect to the variable x. So what you can do, first, look at the parameters here. You can write this polynomial, say minus ax squared plus bx. You can put the minus a in evidence, and you find x squared minus b over a x. All right, this is just an algebraic manipulation here. All right, so one step further, you can complete the square. Say to complete the square here, so minus a x squared plus bx is equal to minus a x squared minus b over a x. And if I want to put x minus something, all of that squared, I must sum the square of this number, b over a squared, and to get the remotion of number 2 here, I need to have an 1/2 for the constant b over a. So squared, you get 1/4. So if I do not change equation, I need to add and subtract the same value. So b squared over 4a squared. And then when you multiply again the a, you'll find minus a x squared minus b over a x plus b squared over 4a squared is just x minus b over 2a squared. This gives you all of that. And if you multiply minus a by minus b squared over 4a squared, you'll find out plus b squared divided by 4a. All right? That's what you find out here. So what you want to integrate is this object. Integrate minus ax squared plus bx integrated over dx is equal to, now if you plug in this polynomial in that form, this factor e to the b squared over 4a does not depend on x, and you can put in front of the integration sign because it's just a constant. And you will need to integrate from minus infinity to infinity exponential of minus a x minus b over 2a squared dx. All right, that's it. That's what you need to integrate. But now you can change variable again. So observe that we can now make the following change. X minus b over 2a is equal to, say, the variable z, and dz is equal to dx because the differential of this thing is just the differential of x, the differential of a constant is 0. So the differentials are equal, and the limits, when you plug in x equals to minus infinity, it's just a numerical value, a finite numerical value, so z is equal to minus infinity. And when you plug in the plus infinity here, z goes to infinity. So this integral here goes to just same limits, but you need just to remove this thing because it's symmetric. It's just a finite value, and you are integrating this from minus infinity to infinity. So you change variable. All right. This way, the integral from minus infinity to plus infinity of this polynomial is equal to e to the b squared over 4a, the integral from minus infinity to infinity exponential of minus a z squared dz. And now you can change variable again. Say u, a variable u, is equal to a z squared. Or perhaps the square root of a multiplying z. All right? This is what we want here. So a z squared is just u. Now, u squared. All right? And the du is equal to the square root of a dz. So, if I multiply the equation by the square root of a and divide all the things by the square root of a, I'm just inserting the unity here, I'll find this is the du, and this thing here is u squared. And that value, we already know what it is. It is just the square root of pi. So, notice now that this integral has the form of e to the minus u squared, u from minus infinity to infinity, provided that this is the du, and minus az squared is u squared. It is the form of the first integral we've met here, so this is just the square root of pi. All right? So a Gaussian has a value. Now I can replace this thing by the value, the precise value. It has this form here. It's equal to the square root of pi over a exponential of plus b squared over 4a. All right? That's it. That's the value we want. Now, look at the following thing. If you want to calculate things like this, x to the n, e to the minus a x squared, say, from minus infinity to infinity. How to proceed? How can you calculate these things? Well, first, there is no b multiplying x here, but just introduce a value here. So what you are performing is the integral in the limit where b goes to 0 of x to the n exponential of minus a x squared dx. Here I must plug in the bx value. We already know what is, with n equals to 0, what is this integral, all right? So we know what I have here, but just say that this integral here, which I want to evaluate, corresponds to this thing here. This integral with the b, it seems to be more complicated than the previous one, but just wait for a moment. I will show that. You plug in a b multiplying x, and in the end of the calculation, take the limit b going to 0. All right? That's a very interesting calculation here. So, if you allow me, I'll do some more steps. Now, notice that the integral of x elevated to the n from minus infinity to infinity of this exponential here can be rewritten as a multiple derivative of the integral with respect to b. All right? Because when you derive to the bx is equal to x with respect to b, the variable b. It's just b here, and it's just x, the constant multiplying b, and repeat the exponential. So if you derive again, you will find the x squared. If you derive again, x cubed, and all that. So the nth derivative with respect to the variable b of this thing here will give this x elevated to the n. All right? But this integral, we already know what it is. We already calculated that. It is just then equal to the nth derivative with respect to the variable b. All right? If you want x here, you derive just one time. Notice that if you derive with respect to the variable b just first derivative, the derivative only applies to this term here, you have an x multiplying the exponential here. So, and b is not a variable of integration, so you can commute the integral with the derivative here. All right, x to the n multiplying e to the bx can be written as the nth derivative with respect to b of this exponential here. But the integral of the derivative of that exponential to get this value here can be commuted, and now the derivative is in front of all that, and this integral is just the Gaussian integral. We already know that. So we will have here the square root of pi over a and the exponential of b squared over 4a. And now, if you are interested in the limit where b goes to 0, you take the limit of this equation here. So if you want that calculated, if you want this thing calculated, xn e to the minus ax plus squared here plus bx integrated over dx, you just need to derive with respect to the variable b here n times to get the momentum. It's called, the powers of n are called the momentum of the Gaussian. The second momentum, first momentum is n equals to 1. Second momentum is n equals to 2. That has nothing to do with the momentum of a particle, right? It's just a jargon in statistics. So the first momentum is the first derivative, the second momentum is the second derivative of this thing here. So as a matter of fact, the square root of pi over a is just a constant, so you can derive just exponential e elevated to b squared over 4a. So if you want to calculate, for instance, the integral of x squared e to the minus ax squared with respect to the variable x, you just need to take the limit b equals to 0, because the limit of this thing when b goes to 0, square root of pi divided by a, the second derivative with respect to the variable b, e to the b squared over 4a. It is called a generator, all right? And in some jargon, b is said to be a source. It is a source generating the momenta, in the statistical sense, and you derive that. Second momenta is second order derivative, and if you plug in a 3 here, the third order derivative, and so on. But you'll find out that for odd values of the n here, you'll find 0, and for even powers of x here, you calculate and take the limit, and you'll find out what is the result. All right, so this is integrals of Gaussians. Also, it's a very interesting result when you are calculating the when you're calculating the Fourier transform, I guess the notebook will shut down because it's in the end of battery, but I guess I can finish here. So if you were calculating, for instance, the Fourier transform of this thing, suppose you have e to the minus x squared divided by twice some value here. I guess I put the a dividing here. So if your function has this form e, and I guess I put in some value for the momentum, a p0 over x here. So if you want to transform this thing, there's a constant here. You need to find out what it is, I guess. But if you want to transform for momentum or for k, the h bar k is equal to momentum. So if you want the function with respect to the k here, you'll need to do this Fourier transform, the integral from minus infinity to infinity. Psi 0 is just a constant here, so it can be put out of the integral, can be put in front of all that, and you find minus x squared over 2a squared e to the I p0x, and here you find it's divided by the h bar here. So you can say p0 over h bar is k0 here. And you need to integrate this thing here. So here you can find what it is, the constants. So it will give you a psi 0 over the square root of 2 pi. You can find what is b. It's, divided by the h bars, the k0 here. So you find that the b is related to an imaginary squared gives minus 1 minus k minus p0 or k0, say, squared. So it's shifted. A phase in the real space corresponds to a shift in the momentum space or the dual space, all right? Divided by 4 times, I'm using the integrals of Gaussians. You have to plug in a square root of pi and divide it by the square root of the a value. So the a value here is 1 over 2a squared, 1 over 2a squared, 1 over 2a squared here, and 1 over 2a squared here. So that's the result. All right? And then you'll find out a square root of 2 cancels out, square root of pi cancels out, you get a psi 0, a multiplied by a, exponential of minus k minus k0 squared divided by twice, and the a squared goes in front, multiplicating here or times. So that's the Gaussian integration of a Gaussian wave packet. I guess that saves the day when talking about solving a problem with a Gaussian wave packet. And now you have found the spectrum in the momentum space. You can now replace the k by p and p0 here because the Broglie relation allow you to do that. And also you can calculate now the averages of momentum squared, operators, of course, and all that. All right. So that's it for now. There are a lot of more results involving the Gaussian of multivariate calculus, but for now, that's what really matters here. I don't know if you are looking properly here. It's just a constant of the function. This is an exponential. And notice that the Fourier transform of a Gaussian is also a Gaussian. But if you take the modulus squared here, the Gaussian has a width in the real space, in the x space, corresponding to this value of a. And in the momentum space, it has the inverse width. So if it's just short. It has a small width in the real space. It will be large in